It's my pleasure to introduce Dr. Casciati, which is a researcher at the University of Catania in the site of Syracuse. And Sara Casciati has large production, scientific production in the field of dynamics, earthquake engineering, and structural control. She is Secretary of the European Association of Structural Control, and she is in the editorial boards of two international journals about smart systems and control. So I think she is a very promising researcher for our field. Therefore, I'm very happy she accepted our invitation to give us a seminar on recent studies for regulation and control of civil engineering structures. Please, Sara.
Thank you very much, Professor, for having me here today. So today's talk will be about the recent studies of structural control of civil engineering structure. And I conceived this lecture for a public from a wide background, so that in 2 hours I didn't want to cover the entire state of the art on structural control, but I'd rather focus on what the international community nowadays think are the most promising technologies for future developments. And we'll anyway start with a brief introduction distinguishing passive from active, semi-active and hybrid control, and among the literature we will select those which we think are more promising for development. And we will emphasize also the necessity of further studies in hybrid systems, which seems to be the combination of the advantages and the overcome of the limitations of all the other types of structural control. And my own background comes from material science, shape memory alloys. So I would devote particular attention toward the end, maybe in the second half of the talk, in order to introduce the topic of shape memory alloys. And we will end up with conclusion. Now, given that the vibration mitigation is a very broad topic which interests a lot of fields in engineering, we would like to stress the necessity to treat structural control for civil engineering apart from the other disciplines, although we need to make the best out of the experience in other fields. Now, the boundary conditions, however, that we need to deal with are quite peculiar, because we are dealing with large, very, very large masses, long lifetimes that are not comparable with the ones of structural control devices, and which require a maintenance plan. And we need to provide, in any case and in any scenario, robustness and safety to our structures, which means that during maintenance the structures still need to be fail-safe, which means that if one of these devices is out of order, we still need to rely on the robustness of the structure itself. Also, other concerns come from the lots of uncertainties that affects the loading condition and the physical quantities which can be due, for example, to the material damage and the state of the structure itself. Also, the dynamics of the actuators and its interaction with the structure is of concern, because there's always a delay between what comes from the actuator and what actually is received from the structure. And this is still a problem to be discussed. Also, the location and the limited number of sensors and actuators are a limitation due to the need of large forces. In the end, the baseline concept of civil structure is that they were conceived as passive structure in the sense they are not adaptable, so that we make designs assumption without actually knowing which one are going to be the loads. So the intent here is to add the devices to the structure, to change the structural configuration, the structural properties, in order to have a better response through the addition of devices. Devices that can be of different types, and they can be active if we are actually exerting a force, a control force on the structure, which however has the big drawback that it needs external power. And when exceptional loads occur, the first thing we do is run out of current. So we need to make up for this. Passive control instead use energy dissipation devices which produce the control force as driven by the structure motion. So of course they're less adaptable. A good compromise is the semi-active control system, which are receiving a lot of attention lately. And actually what they are, they make passive devices adaptable, so that they tune the properties of the design device to make up for the recorded response. Finally, hybrid control is a step forward in semi-active because it actually combines both active and passive control system or base isolation. And the portion of control is accomplished by the passive system, so that we can always rely on that even if there is no power. And it seems to be a promising way to actually merge the advantage of the other world and overcome their limitation. From a mathematical point of view, starting from the basic example of a single degree of freedom system, the structure is described by the equation of motion, and here we are assuming as the external force the ground acceleration due to earthquake. But in general, this one can be extended to any extraordinary loads during the structure lifetime. When the structure is controlled by passive system, the passive system does change the structural response by adding a term, which is this gamma x, which can take different forms, which might be linear, might be integral, might be differential. And what makes this system passive is that this is decided by the designer and cannot be changed. So when we move on to a semi-active strategy, or to a fully active one, or even the one that makes use of both, the gamma x term is replaced by the control force. The control force has the same role of changing the structure response in terms of stiffness or damping or even mass, but it can do it in an adaptive manner. Based on what? Based on the response that is monitored, recorded during the structure and during the extraordinary event. So in order to schematize the difference between the different strategies to protect the structure through control schemes, we see how a conventional structure is usually undergoes an excitation. So it can be seen like the system that transfers the input signal into the response one, into the output one. The passive systems are actually integrated into the structure because they do change the structural features. So it is an integration of devices that changes either the damping, the mass, or the frequency in order to avoid the resonance phenomena. Usually it's easier to change the damping than the stiffness, and that's what they usually do. When we pass to a completely active solution instead, we add more things on our structure. We have to add more devices, sensors, controllers, and actuators in order to form the so-called closed loop or feedback control, in which the sensors are used not to measure the excitation, because as we say, during the lifetime of a structure, extraordinary loads cannot be measured in advance, but to measure the response. And based on this response, the controller will have to compute the control force that the actuator will exert on the structure in order to correct this response. So the problem of active control is an optimization problem, because we need to find the compromise between a better response and the cost of the active control device in terms of power and capabilities. The difference between what we call active control and hybrid control is that hybrid control also relies to passive devices. Passive devices that are integrated into the structure, changing its configuration, so that if the control actuators are not in functioning, we can still rely on the passive part. What is the difference with the hybrid? So with the semi-active solution, the semi-active solution is when the passive energy dissipator is integrated in the controller and not into the structure. And this is because the controller is used to tune the properties of the passive device in order to make it become adaptive. The passive device can also be an isolation system. Here, to conclude this brief introduction, we have a summary of the protective systems that are nowadays in use in civil engineering. And if we want to also have a regional discussion of their use, unfortunately we have to establish that in Italy the only one that is mostly used is seismic isolation. Now, seismic isolation is passive and has the drawback that is targeted only to the earthquake action. So we say we want the structure to be adaptable to any kind of loads, but seismic isolation works only for earthquake. And not only, if you have to do seismic isolation on an existing structure, this is very expensive. You need excavation. It's effective though, because experience shows that after an earthquake, seismic isolation for structure worked well. The other passive systems include dampers, which can work on different principles in order to dissipate energies. And they can be metallic, or friction, or viscoelastic, or fluids. Among the active and semi-active solution, we distinguish the purely active ones, based, for example, on active mass dampers, to smart materials, which are instead more in the semi-active area, because they are material with functional properties which can be tunable through providing electricity. The hybrid system is a combination, as we say, of both the passive world and the semi-active or active one. And it has the advantages of lower power requirement and to be potentially fail-safe. Whereas the passive structural devices are more reliable but cannot adapt, whereas the active rely on too large power inputs. So the advantage of hybrid system over the passive one are adaptability, enhancing the effectiveness in the response modification, the applicability to multi-hazards, so not only earthquakes, and the selectivity of the control objective. Here are some examples from literature of hybrid system, and those are actually being implemented in real buildings in Japan. In terms of diffusion, as we say, in Italy we only have seismic isolation, or at least at most seismic isolated structures. But in Japan, actively protected buildings are of common use. And this is, for example, a hybrid active pendulum in which the control force is used to drive the motion of the pendulum. Here is another hybrid system in which you have a duox system in which we have a AMD at top of a passive element. Another innovative device that are now being studied a lot are the so-called active isolators, in which you combine seismic isolation with some kind of active or semi-active dampers. Those are examples from the past. A more recent one is the TV tower recently built in China, in Guangzhou, where it was implemented a hybrid system. This is in a region which is very prone to typhoons, so strong winds, and they equip both the structure and the antenna with two different isolation systems which are based on hybrid control. The combination of tuned mass dampers, which are the columns full of liquid, which however have a limited stroke. This stroke enables these TMD devices to be reactive only to limited weak wind velocity, low wind velocity. When there is a typhoon or this wind velocity is stronger, the active part of the structure comes along and provides for the missing capacity. And this is another promising device, which is a hybrid platform for seismic isolation, and it also shouldn't be used only for structural elements, but also for non-structural elements, for critical equipments. So we are talking to protect critical buildings like hospital or government, and the devices are not only concerned to the structural safety, but also to the equipment inside of the building. Now let's go a little bit more in detail into, we saw some hybrid solution, but before discussing the hybrid we need to understand the active. The active was implemented in many different Japan buildings, we say, and here is the first one, was in 1989. And active control actually had his pioneer, Professor Kobori, who started studying the problem in the 70s. The problem with this solution, though, why is hybrid better? Because when there is loss of power, the actuators do not work. So in the last earthquakes, in Kobe earthquake, the actuators did not activate it. And so we have to combine this with passive solution. The unsolved issues are also the maintenance frequency, the safety of the structural system, which always needs to be preserved also during maintenance, the time delays between the actuator and the actual controller, and the robustness of the structure itself. Those are the open issues. The recent studies were successful in developing new technology, digital type, sensor with the desired resolution, and actuators of non-hydraulic type so that they can actuate also during an emergency like an earthquake. And then we also had more studies pursuing integrated design between the devices and the structures, and system identification methods which need to work in large deformation, because active control, since it's expensive in terms of maintenance and power, needs to be activated only as the last reserve, only when we have the earthquake striking and we are in large displacement. So we need system identification methods that work for highly nonlinear structure, as we will see in a moment. And then there is the need also to develop for a complex structural system some model order reduction techniques. So, an example of system identification techniques that is realistically applicable during an emergency. We say it's the last resort during a significant nonlinear deformation. During this deformation, the system usually shows a behavior that is highly nonlinear, is hysteretics. Hysteretics means that the restoring force is dependent on the past history of the state variables. Therefore, we need an online parameter estimation techniques which tracks the evolving structural properties, and as output of these tracking techniques we will calculate the controlling force through an efficient control algorithm. So we start by considering a simple single degree of freedom system, which is hysteretic in behavior, highly nonlinear, where the nonlinearity is represented by these terms, which is the nonlinear restoring force, and depends on both the position x and the velocity of the single degree of freedom system, which has represented by a mass m, and is subjected to an external excitation, which is an extraordinary load varying with time f of t. Now we can express the evolution in time of the restoring force by means of the well-known Book-Wen model. The Book-Wen model is very used because it is highly flexible, in the sense that it can keep track of the hysteretic loops of different shapes, which can range from a fully non-elastoplastic system to polynomial-like nonlinearities. And it depends on several parameters which dictate the shape of the hysteresis loop. These parameters are named here in red. Now, if we want our model to become even more flexible and include even larger classes of hysteretic system, we can add to the restoring force, which now we call zeta, but is equal to r, just because in literature they refer to it as zeta, and is given from the equation of motion by f minus m by the acceleration. This parameter we add to the terms that comes from the integration in time of the Book-Wen model, also two other terms. One that is proportional to the velocity, and another that is proportional to the cubic of the position. And so that we introduce two further parameters to be identified. So the objective of our tracking solution in time is to identify the vector of unknown parameters that describes our restoring force model. We take the derivative on time, and we have the dependencies on the factor k CD. One notes that k came in from the previous expression of the Book-Wen model because it just takes the place of 1 over eta by a, divided by a, so it's not a further parameter, whereas c and d are the newly introduced ones. And then we have the cluster of the remaining parameters and the exponent n. N appears nonlinearly because it is an exponent. So that in order to circumvent the problem of identifying n, which appears nonlinearly, we replace it with a series of truncated terms. And we introduce, instead of n, the summation over a number of finite points where uppercase n is user-defined, of a terms multiplied by a binary coefficient, an, which is the newly introduced coefficient. It's binary, it's either 0 or 1. So if that exponent n influence the model, it will take the value of 1. If instead the model is not influenced by it, it will disappear and take the value of 0. Repeating this procedure in the identification procedures, one finds that there is no need to go over n equal to 3 in order to represent any mechanical system, so that our series is actually made on only 3 terms by 2 coefficients, so it's going to be other further 6 coefficients to be estimated. Finally, this is the vector of the unknown parameters to be estimated through our online procedures. And this is the estimation algorithm, where the estimation model says that the signal, the filtered signal zeta, his estimate is equal to the product between the parameter of the unknown parameters, and the vector that collects the state variables. on which we applied anyway some low-order filters. The low-order filter that depends on the Laplacian variables, and they're introduced to eliminate the noise through a low-pass filter. Then we introduce the gain matrix, and we solve the optimization problem by introducing the error between the filter response and the estimated response. So that for each time t, we obtain an estimate of the parameters which varies with the load. And we follow the hysteretic cycle. So here are the results of some numerical simulations. So far the system, which is hysteretic, is not controlled, is uncontrolled, and the equation of motion is simply this one. To test that our algorithm works, we tested on a baseline configuration in which we have an external excitation which is simply sinusoidal. And we see that the estimation procedure converges within 35 seconds. So here is the actual values of the parameters. The correct values are fully reached within the first 35 seconds of the excitation. And here is plotted the restoring force R, which is given by this model, where the parameters are substituted step by step in time, plotted against the displacement x of our system. Now let's introduce the control law. The control law is introduced by three feedbacks, one on the position, one on the velocity, and one on the error between the external force and the restoring one. And we see how the introduction in the equation of motion of this control force will actually improve the response in terms of decreasing the amplitude of the displacement. So we compute the response to an impulse input, and we obtain the uncontrolled response and compare it with the one in which we have only two controllers, the one on the position and the one on the velocity, and eventually the red one when we account also for the difference between the external force and the restoring one. And we see how the three feedback controller is much more effective than the other one, and so we keep all three feedbacks in our controller. So it's a controller design in the end. Now we move from the academic case to the one that is more realistic, a random excitation, which could be representative of an earthquake or also ambient vibration. And in this case, the solution of the tracking parameters algorithms converge within the first 15 seconds of the excitation. And here we compare once again the response without the control force in blue, and the green one is when we activate the controller. So here was just to have an idea of the software, of the control law that we need in practical application. But control is a multidisciplinary sector in which you also have to look at the hardware. And nowadays, we were trying to summarize before, studies led to the development of wireless technology. Wireless technology, which is very convenient in terms of installation and also, why not, sometimes also on performance. But our controller needs to be remain the same reliability as before. So we need to update our control system to give us the same results that we had when cables were utilized. So we did design this wireless sensing unit in this spirit. We do not want to add computational capacity to our control system. We only want to replace cables so that our controller can still work on the same reliability requirements, and we only need to change the transfer data part and the data acquisition. I would not go into the electronics details, but it's only to say that this was a customized solution, that in order to go wireless you do not have to rely on commercial off-the-shelf solutions that are very, very expensive, and many people would not adapt them. Because why? Because they don't guarantee that your system will work as before. This is a convenient, easy solution in order to keep your equipment as it was before the cable were removed. Here are the components of the laboratory mock-up, and it's a small scale. We're going to see that again, steel frame mounted on a small size shaking table, which is monitored by accelerometers, which monitor the response of the structure and give it as feedback to the controller, who computes, as we said, an optimization problem and the control force, which is good enough to improve the performance but doesn't require too much power to do it. And this control force is used to move through a servo-hydraulic motor a mass on top of the steel frame through a rail, and the control system that are implemented here are both a standard linear quadratic Gaussian algorithm or a control algorithm of fuzzy type. In both cases, we proved that passing from wired to wireless solution, the efficacy of the controller algorithm, both of them, is still valid, and the amplitude of the oscillation due to a sine wave near to the resonance are decreased by the active mass damper. Okay, so this is for active control. Let's move over to semi-active devices. Semi-active devices are receiving a lot of attention because, as we said, active control proved not to be reliable alone during earthquakes. And semi-active devices, the ones that are listed here are the traditional one from literature and are based on a valve. If this valve is open and the liquid or the material can go through, then we are tuning the properties of the device by varying its damping capacity. If the valve is closed, it's still a passive device. So the minimum performance you can get from a semi-active device is the passive one. But with respect to the passive one, we have the advantage of being adaptable, having lower power requirements with respect to the active system, being fail-safe, because if the active device fails, there's still the passive one working, providing a better performance than the passive one, but potentially can also reach the performance of a fully active system. What are recent studies focused on? The adoption of a semi-active device, as we say, has a lot of advantage, but they're basically nonlinear devices. So you're adding nonlinearities to your structures. So you need to characterize these devices from a structure-device interaction point of view. Not only we have to discuss the location of the devices across the structure and the issues inherent to the control load, which is used to tune their properties in order to avoid possible delays. The advantage is we're not adding any mechanical energy to the system, and so it's not going to become unstable because of these. Among the ones in literature, we agreed with This is actually studies that are being carried out in California by Professor Sami Masri. One of the most promising ones are the impact dampers. He's been studying them with Timoshenko since 1972. This is likely nonlinear auxiliary mass dampers, which means that the dampers incorporate a secondary system which relies on some resilient stops to clip the relative motion between the primary and the secondary systems. Now, according on the parameters that we're using, we can classify them into different devices. So if the secondary system is connected to the other one through only a spring but not a damping, then in this case it's called a dynamic vibration neutralizer. If instead there is no spring between the primary and the secondary system, we have the Lanchester damper. And this is always in the case in which the span of which the mass can relatively move to each other is comparable to the displacement of the primary system. If this distance d is instead of the same size of the primary system and it is there is no damping and secondary stiffness, then we have the simple impact damper. These properties can be tuned by simply adding a semi-active algorithm, and in this way we can also vary the activation level of the distance d, as well as the coupling mechanism between the primary and the secondary system. So whereas this is the passive version, if we add this control algorithm we will achieve the semi-active version of it. Now, one tempting feature of these devices are the fact that they provide ideal conditions when we have systems that are characterized by roughness and you need the requirements of reliability and sensitivity to exterior temperature. But they also present some undesirable characteristics because we are treating with impulsive loads which exchange between the coupled system. There is the noise that potentially can be against the comfort of the construction. And then there is the dependence of the optimum gap on the damping force. It was proven that a more advantageous solution could be obtained by coupling together different impact dampers working in parallel with each other, so to have a multiple unit. In this way it's proven both experimentally and analytically in literature that we can have a reduction of peak impulsive damping force, a lessening of the noise pollution, and a reduced sensitivity to the gap size. Now here is the curve that shows the decrease, the sensitivity of the damping from the size of D by adding another impact damper in parallel to the previous one. If we keep adding them, we obtain the so-called particle dampers of granular type, which are being studied now in Japan with some successful results. Here are the results from experiments where the dampers actually reduce the top displacement of a multi-story building, and they work in parallel of several units. In this way you reduce the noise and you reduce the dependency on the gap size of the damping effect. However, it is a very complicated system because even if you have only one particle, the motion can be of chaotic type. So when you have more than one, the problem becomes very complicated to be governed analytically. What is the future perspective of this kind of dampers? Let's move from a discrete granular material to a continuous one. How? By introducing some advanced material of composite nature, which are provided with microchannels tuned so that they give us the same functionality of the particle system. And this is current research going on nowadays at University of California. Another example of promising semi-active device, which is being deployed intensively in the Asian countries, are the magnetorological type. They're called smart material because we can tune the properties by simply varying with an electrical field, or in this case, we vary the magnetic field, and by adding magnetic field, we increase the capacity of damping, of dissipating energy of the device. And they can be installed either on stay cables of bridges to counteract the wind forces, or as braces in bridges in a building for earthquake protection. But my main expertise, they say, is on another kind of smart material, which is shape memory alloy. What we push to do is the same type of application of the magnetorological dampers, but with shape memory alloys. So the magnetorological dampers, I'm not going in details, but the key feature is to change the magnetic field in order to increase the damping capacity. Shape memory alloy, you change the transition phase, you transition between one solid state and another. How? By either impose temperature gradient or by imposing a mechanical stress. Now, sometimes when we talk about shape memory alloy, everybody just thinks about the shape memory effect. This is one of the possible functional properties that you can exploit of shape memory alloys. And it's given only for, it's used only for some kind of application which are of actuation type. So when you think about shape memory alloys, some people associate it automatically to actuator, active control. The application that I would like to talk to you about instead is the equivalent of the magnetorological damper. So it's a damping device. It is based on the superelastic properties, which is shown in a different range of stress and temperature with respect to the shape memory effect. So the shape memory effect consists, briefly, just to have a brief introduction of shape memory alloy, the two fundamental states called parent states or austenite and the martensite states are achieved at a different level of temperature, we say, and at a different level of stress. The difference is that the parent austenite is rigid and well organized in cubic form. Instead, the martensite is more like a plastic deformation and can be oriented or not according if we are working at low level of stress or at a high level of stress. At low level of stress, the twinned martensite accommodates into austenite, so you don't really feel the change of shape with respect to austenite. Instead, when you go in higher level of stress, the orientation of the martensite also causes a change of shape with respect to the austenite parents. At the thermodynamic point of view, these two stages are characterized by some transition from a starting temperature and a final temperature, where the austenite is achieved at higher temperature, whereas the martensite is achieved at a lower range of temperature. So MS, for example, indicates the temperature at which the transformation from austenite to martensite starts, and MF indicates when it ends. The actuation effect of shade memory alloy, the so-called shade memory effect, is based on this second phase, the martensite. In this range, we say, of both stress and temperature, those indeed should be plotted in 3 dimensions to take into account both the thermal and the mechanical effects, are that when you unload the stress on a martensite alloy, there is, by heating, the possibility of going back to the undeformed shape. This heating causes a stress, which is the actuating stress that can be used for actuating at low level of forces, of course. Whereas when we are in austenite phase, during the unloading, there is the mechanical transformation, no longer the thermal, in which the austenite, the initial elastic phase, is in austenite, then starts turning into martensite, and we have this increasing plateau, and then during the unloading we have the inverse transformation. As a result, we have a loop whose area can be used to dissipate energies and be transformed into mechanical, into heat. So those are the basic principles, and I would like to stress the fact that we would like to use them at damper, which means use the superelastic property of it. Which means we need to be in austenite phase, because for this diagram to apply, we need to be above AS, above the temperature for which austenite temperature starts. So the first thing we need to do is choose the alloy composition. The most utilized alloy is the one based on nickel titanium. The one based on nickel titanium offers some very advantageous properties, which are a very long fatigue life, for example, durability, not corrosion. But on the other side, they have a narrow window, which is at high temperature. So we did not limit ourselves to study only nickel titanium, but we consider also the possibility of applying another kind of alloy, which is copper based, aluminium, beryllium, copper, which have a temperature range of austenite which is more suitable to civil engineering application, because it's comprises between -20 and +2 degrees. On the other side, the fatigue life is lower and it can be corroded. So the early studies were based on nickel titanium alloys, and they were carried out within an FP5 project, so we're talking about 2001, and the alloy was used to, let's say, sew together masonry blocks of very ancient monuments. So the intent of this research project was cultural heritage preservation, and one of the most interesting case studies was the preservation of the Luxor Memnon Colossi in Egypt. And you see how they lay in a degraded state, where the basement is affected by passing cracks. So the idea here was to sew together the cracks with shape memory alloys wire so that we limit the relative displacement during an earthquake. But at the same time, we don't add too much stiffness, like if we were going to use iron. But we still enable dissipation of energy. The model was schematized by finite element, where the cracks were included by modeling a contact problem. And here is shown the relative displacement of two nodes at opposite edges of the cracks, with and without a link of a wire who had the constitutive law of a bilinear nickel-titanium shape memory alloy. And we see how the relative displacement with the addition of this device is limited compared than the case without it. But we have the drawback that nickel-titanium only work for this austenite window, which is not very suitable, especially in the desert, which have very big gradients from the night to the day. So we moved to study the behavior of the copper-based alloy, which has a better austenite window in which we can exploit the superelastic properties. The earliest study on copper-based alloys were first based on simple material testing of loading and unloading, and here is shown how the constitutive law depends not only on temperature. You see how the possibility of dissipating energies narrows and becomes less as the temperature increases, but also with the frequency of or speed in which the loading and unloading cycles are applied. So these were the results of tests of traction and compression in an M&MoCS machine. Now we move on the same model structure that we use for our active control test. And we mounted the wires in copper base as braces on the first floor. We compared the response not only without the braces, but also by replacing the shape memory alloy braces with the steel ones. Here are the results with steel braces, and here are the results with the shape memory alloy. And you see how we have not only a better damper, but also a higher reduction capabilities. Similar experiments were conducted by mounting the shape memory alloys in order to form some sort of composite material. So for example, here we combined it with the steel, and we made the columns of this single degree of freedom steel frame made of composite shape memory alloy and steel. We can see how the frequency of the spectrum changes with the introduction of the shape memory alloys plates, but doesn't make also much sense to talk about frequency because the system becomes nonlinear. And so we try to characterize the nonlinearities of the system by conducting experiments of increasing amplitude and then decreasing the amplitude. You see how the shift of the peak indicates that there are some nonlinearities affecting the behavior, dynamic behavior of the structure. So combination of shape memory alloy with steel and combination with wood. Here is also an impact phenomenon that we studied because we use the shape memory alloys as connection in the form of bolts that are inserted in the joint between a column and a beam of a wooden frame. So the major problem with wood structure is that their joints are too rigid during earthquakes. So here we're studying a smart joint that during the earthquake loosen the capacity of the joint the connection, and creates a game between the hole hosting the connection and the bolt itself. And we repeated it using both steel bolts and shape memory alloy bolts. And we compare the results that are with steel bolt, still the frequency in the feed, in the forward and backward test are the same, whereas you can see a clear shift when you introduce the impact bolt in shape memory alloy. And also the studies need also to take into account the impacts between the hosting hole and the shape memory alloy device itself. Moving to more practical application, which were the original one, we remember, were targeted to monuments. Monuments, we can always assume that they are assemblage of stones. So in order to model the capacity of holding these stones together by shape memory alloy wires, we mounted a specimen of masonry where the masonry is loosened. So here we have no linearities that are geometrically introduced by the fact that there is no connectivity between the bricks. And we repeated the shaking table test on the loosened bricks, which are held together only by the compressive force of the pressure of the plate at top. And then we introduce the shape memory alloy wires between the top and the bottom plates. And we analyze the results also from a numerical point of view. Why? Because we want to understand how we can model the structure, including the shape memory alloy device, without changing the dynamic response of the structure, by actually representing the experimental results. So how do we obtain, for example, the same frequencies and the same maximum displacement that we obtain from our shaking table test? This is preliminary study for designing our intervention retrofit on monuments, because in this way, once we establish how to model numerically our devices, we can design how many devices we need and where they need to be located without having to run too expensive analysis. And those are two other case studies. One, the Cyprus Aqueduct, they actually implemented the retrofitting, and it's still there and is being monitored. And there are students that are still analyzing the measurements of the retrofitted aqueduct. The Civic Tower of Soncino instead was the object of a monitoring campaign. It has not been retrofitted, it's still affected by pretty serious cracks. But here was at least a proposal of retrofit where these devices were to be inserted where major damage was caused by the passing cracks. And we see how the experimental results once again could match the numerical ones. Another more similar to magnetrological device application are the braces in steel frames, which are also modeled numerically and experimentally. So the braces in shape memory alloy really have a significant damping effect and enables, in this case, to reduce the amplitude of the oscillation. They drop from 1.5 to 0.3. And this is the mounting device, because in order to achieve the superelastic behavior, you need to reach the plateau, which means you have to go over the initial elastic phase. In order to reach the plateau, which also means you can recenter your device, you need to give it an initial pre-stress. And this is the device that we use in order to install and give the pre-stress to the device. So this one was a seismic application. Here is the application for cable stays in bridges, which has different requirements because the problem is very different. The number of cycles that the structure needs to survive in this kind of application, the fatigue life must be much longer than for an earthquake. But on the other side, the deformation levels that you're working with are much lower. So in any case, you can still survive 1 million of cycles with this device using the entire fatigue life. Also notice like you cannot rely anymore on the big entire cycle that you had for the earthquake case, because when you go in earthquake, the maximum deformation here is around 8%. So you're relying on a bigger cycle. Here, when we have wind application, the deformation is about 2% or lower. So you can rely on smaller energy dissipation capacity. Here is a plot that shows how the energy varies with the deformation in millimeters, so the elongation to be precise. This is a small-scale experiment that is being conducted at our laboratory, in which we have a teeny steel cable with the distributed lumped mass along it, and we did apply the shape memory alloy device coupled to it next to the excitation, and these are the experimental results. We are now working on the numerical part because it's not very immediate to also model the phenomenon of interaction between these concentrated masses and the cable itself. So there is an interaction also within the cable. But the main issue, we are carrying out this reduced scale experiment, is to understand the scalability of the results. Because what we obtain here are for reduced scale spacing. Ho quasi finito. So how can our laboratory results be extended to realistic results of cable of real size, which have a length of 50 meters and a diameter of 50 centimeters, compared to instead our laboratory specimen of before? Why do we want to do that? Because we are creating virtual laboratories in which we want to be able to perform as many inexpensive experiments on laboratory scale and be able to extend them to the real world. So we have to compare the scalability of the results. And these are the results obtained from a bigger facility, which is the JRC in Istra in Varese, where you can see that also in the case where there is no shape memory alloy devices inserted, there is a strong damping, which is not typical of cables, because usually cables have no damping at all. Why is that? Because these cables are full of wax. So we learned that they are already dampened. Instead, a cable which is not full of wax, so it has no damping, is the one in IFSTAR NANS, which is the LCPC. And you can see how there is no damping, or natural damping occurring here. Now, when we add For example, here was a sinusoidal external excitation. Here was a heavy side function, so an impulse function that we exerted on the cable. And we see how the insertion of the smart damper can reduce the amplitudes and can add the damping to the structure. But the most interesting results here, we said, before we were working at deformation level of 8%, which are typical of earthquake engineering. Here we're working at the lower level of deformation. At lower level of deformation, we obtain numerical results that are more similar to the experimental one when we do not adopt the bilinear model. The bilinear model gives very good results for earthquake engineering. And that's the one that typically we adopt when we have the uniaxial case of shape memory alloy that is a wire. But when we use lower level of deformation, to obtain a good agreement with the experimental results, it's better to go on a cubic feet. And in this case, we can actually obtain the realistic energy dissipation capacity of the device. Instead, if we rely on the bilinear model, we overestimate our damping capacity. Non so questo perché è uscito. Scusate.
Nulla.
Ok, non so. My presentation covered a brief overview of recent study in control. Rather than pursuing an extended state-of-the-art, which was not feasible in a couple of hours, we focus on particular cases that are judged promising for future development and future research. We invite anyone interested into the topic to submit a journal article and participate to conference. The next one will be the World Conference on Structural Control to be held in Barcelona in 2014 on July 15-17. And here is our new president from this year, not only of the European Society but also of the international one, because Professor Fujino just passed over the precedence to him. So for the coming 4 years, Europe will lead both the international and the European community on structural control under the auspices of Professor Rodella. And we all hope to see you there. And of course, if you're interested in joining the association, we have a website you can refer to. Thank you very much for your attention.
Now we have a minute for discussion. Are there any questions about this conference? Can you tell us something about from a numerical point of view? I think that the only possibility we have is to attack the problem numerically. Probably it's too complicated for an analytical solution. Is it the truth?
Yes, and the state, the control, access control, I guess you're referring to, is an optimization problem. So we always need to rely on compromise, so an approximate solution that can only be achieved numerically.
Is there some specific point, some specific difficulties in attacking the problem with respect to the classical methods, numerical analysis? Are there some intrinsic numerical problems in
between the actuators and the structure is not something that I covered during this presentation. It's the dynamics of the actuator itself. numerical complexity, which turns out to be tiny ways, which are very difficult to source of the
Are there some other questions? No one? Okay, thank you again. Sandra, see you again.